Okay, so last couple of days we've been talking about this latent heat thing, okay? And we've said that it's the potential thermal energy that is stored in, for all intents and purposes for us, water vapor, okay? And it can be moved around the globe by wind, right? When it reaches a new place, the water vapor condenses and it releases all of this stored or latent energy, right, into that new environment, raising the temperature in that area. All right. What we want to do now is look at how much energy are we talking about, right? Because I mean, it doesn't seem like very much when you think about, well, all this water vapor is moving from one place to another, okay? But when you realize just how much energy it takes to evaporate water, okay, we're talking about a lot of energy. All right, that's why I said several times it is the second biggest energy transfer mechanism behind what? Convection. Right, behind convection. Convection is the number one. Okay, mostly because it also helps to carry the latent heat around. Okay, but latent heat in and of itself represents huge amounts of energy being moved from place to place. All right, so latent heat has to do with this diagram here on the right. All right, we call this the heating curve of water. It tells us essentially what happens to the temperature of water as you add energy evenly to it over time. Everybody with me on that? All right, so if I start out down here at minus 25, obviously I have water in a solid form. Okay, I have ice. As I add energy to it, what happens to the ice? Well, before it turns to water, it's got to warm up. Okay, you can't melt ice at minus 25. The ice has to be what temperature before it'll melt? 0. All right, so as I add energy, the temperature of the ice changes. Okay, now how would I calculate how much energy would be needed here if, let's say, I had 500 grams of ice? Okay, I'm changing the temperature. Do I have a formula that calculates energy and has mass and temperature in it? Okay, that's the one we've been working on, right? Okay, I have E equals mc delta T. Anywhere where temperature is changing, I can use that formula to calculate how much energy would be needed to make that temperature change. All right, so in this case, I've got 500 grams of ice. Okay, and the specific heat capacity of ice is 2.116, right? On your Okay, well, it's actually 2.116. Anyway, okay, that's what we got, joules per gram degree Celsius. And then I'm raising it from minus 25 to what temperature? 0. It's only ice until it gets to 0, then it isn't ice anymore. All right, then I would have to use a different heat capacity because now it will be water. Okay. So my temperature change is 25 degrees Celsius. So this will tell me how much energy it takes to get the ice warm enough that it'll start to melt. All right, so if we punch in those numbers, okay, we're looking at okay, 26,450 joules. Okay. What kind of thermal energy did I change if I changed the temperature? Did I change kinetic thermal energy or potential thermal energy? Kinetic. Okay? When the temperature changes, does that make the molecules move faster? Yes. Okay? When I change the potential thermal energy, I make the molecules get further apart. Everybody follow? When I change state from ice, where the molecules are tightly packed, into water, they move apart. Everybody with me? Well, with water, that's not exactly true, okay? But they're in a rigid crystalline structure when they're ice, okay? And when they go into water, they're fluid then. Okay, so that's the first part of this. Now, I'm right here. I'm at 0 degrees Celsius, and I keep adding heat. But for some reason, the temperature doesn't change, even though I continue to add heat. Why doesn't the temperature change? What's happening at 0 degrees Celsius while I'm adding heat? The ice is melting. Okay? Ice will not change temperature until it is completely melted. Once you get it to 0, that is. Okay? Once you get ice to 0 degrees Celsius, the ice-water mixture stays at 0 degrees Celsius until all the ice is gone. Then it will start to change temperature again. The weird thing about thermal energy is that you can't change potential potential and kinetic thermal energy at the same time. You're either changing one or the other. Okay? It's not like mechanical energy where you could change kinetic and potential at the same time. Thermal, you can't. It's one or the other. Okay? So once I get this ice to 0, its temperature will remain 0 until all of it is melted. Okay? Is that why we put ice in drinks? Right? You put the ice in drinks, and it absorbs lots of energy from the drink and lowers its temperature, okay, down to pretty much close to 0. Right? I mean, in reality, it's like 4 or 3 degrees, something like that, but you get the idea. Everybody okay with that? Okay. How am I going to figure out how much energy is required here? I can't use this formula because the temperature is not changing, is it? But I still need to figure out how much energy is involved. Okay? That's where latent heat comes in. Right? There are two kinds of latent heat. There's specific latent heat of fusion, which we abbreviate LF. That is essentially the amount of energy required to change the state of 1 gram of ice into 1 gram of water. Okay? That's the specific latent heat of fusion. Right? The specific latent heat of vaporization is the amount of energy required to vaporize 1 gram of water into 1 gram of steam, okay, at 100 degrees Celsius. And this one obviously occurs at 0. Okay. Everybody with me so far? Okay. I'm just going to copy this stuff over here. Oh, I don't want that. Okay, so we have that calculation that we had done before, okay, and that told us how much energy was required to raise the temperature of the ice. Okay, that's the easy part. Now, I have to calculate how much energy is required to melt the ice. That's in my second step there. Right? So in that, I use this formula right here. The energy required to change the state of water is equal to the mass of the water times the latent heat of fusion. For ice, okay, for water, the latent heat of fusion is 333 joules per gram. All right, so imagine this. You have 1 gram of ice. That is an ice cube that has only 1 milliliter of water in it. Okay, is 1 milliliter very much? No, it's an incredibly small amount of water. Okay, 1 milliliter of water, okay, frozen in ice, will require 333 joules of energy to melt it if it is already at 0 degrees Celsius. Okay, does it take a lot of energy to change the state of something? Yeah, it does. All right, so we've already figured out how much energy was required for this first step. Now we're going to calculate how much energy is required for that second step. Okay, so to do that, we're going to go E equals MLF. And we said our mass of ice here was 500 grams, and we're going to multiply that by the latent heat of fusion, 333 joules per gram. Everybody with me so far? Yeah? Okay. All right, 166,500 joules. Okay. Does that seem like a lot of energy? It is. All right, imagine, guys, that's like if you took a half a liter of water. So that's about, if this was full, that's about a half a liter of water. Okay, frozen solid. Now imagine if you had to melt that with your hands. Okay, how cold would your hands get? Very cold, because the energy to melt the ice is coming from where? From your body, from your hands. Okay, it would take a lot of energy. You would probably start to feel cold if you held on to that much ice for long enough to melt it all. Agreed? Okay, it would take a lot, or if, worse, you put it like under your arm. Okay, like you would feel really cold. It would take a lot of energy from your body in order to make that happen. Right? So it takes a lot of energy to change the state of something, and that's just for melting. Vaporizing is even more. Right? And that's why we were saying latent heat represents a lot of energy transfer in a global system. Okay, everybody good so far? So on this heating curve of water, we now have put in a fair amount of energy, and we have raised the temperature of the ice to 0 and then melted the ice. So now we sit right here. If I continue to add heat, what will happen to the water? Right, its kinetic thermal energy will change. In other words, its temperature is going to go up. Yeah, it's going to increase. Can I calculate the amount of energy needed to heat this water from 0 degrees to 100 degrees? Okay, what formula do we use for that? E equals mc delta T, because it's got temperature change in it. All right, so we go down to there. Okay, E equals mc delta T. 500 grams of water times the specific heat capacity of water now, 4.2, times 100 degrees Celsius. Okay, so 500 times 4.2 times 100. Okay, 210,000 joules. Okay, it's barely more than it took to melt the ice. Okay, to heat 500 grams of water, that's half a liter of water, from 0 to 100 degrees, takes just a little bit more energy than melting that same amount of water, or melting that same amount of ice. Okay, so it's changing kinetic thermal energy is a lot easier than changing potential thermal energy. All right, 210,000 joules. Now, the water gets to 100 degrees Celsius. What does it start to do? It starts to boil. Okay, boiling is an indication that we are now changing what kind of energy? Potential. All right, because once water reaches 100 degrees Celsius, it will not get any hotter. Liquid water will not get hotter than that under standard conditions. Okay, that means you don't have it in a pressure cooker. All right, so open to the air, water will stay at 100 degrees Celsius and boil and boil and boil until it is all gone. Okay, in which case now all of that water is vapor, right? I mean, it's not gone, it's just turned into a vapor. You would have to capture the gas and hold it. Okay, so I need to figure out how to calculate how much energy this requires. Does it look like it's a lot, according to that graph? It does, right? I mean, this is saying temperature on this side, and this is saying heat added. So the temperature's not changing, but I'm adding tons and tons of heat, right? I add heat for a long time with no temperature change. It takes a long time to boil off water, okay? You probably know that if you ever accidentally boiled off a whole pot of water, okay? And then you start smelling that awful metallic burning smell in your house as your pan starts to corrode on the, yeah, it's ugly. Okay, so the next one here, specific latent heat of vaporization happens when something is boiling or condensing. Okay, if you want to boil it and turn it into a vapor, you got to put the energy in. If it's condensing and going back to a liquid, then it's giving that energy back off. Okay, something you might have been taught when you were a kid. Which will burn you worse, steam or water? Okay, steam always burns you worse. Partly because steam is obviously a little hotter than water is. Okay, but let's say since both steam and water can exist at 100 degrees Celsius, let's say they're the same temperature. Which burns you worse? The steam. Even though the steam and the water are the same temperature, the steam will burn you worse because it has more what? It's got more energy. Look at this graph. This graph says that steam over here at 100 degrees has more energy than water does at 100 degrees. A lot more. Okay? So what happens is if you stick your arm over, with the kettle, okay, and the kettle's spitting out the steam, and some of that steam gets on your arm, not only is it at least 100 degrees Celsius, but as soon as it hits your arm, what does the steam do? Is your arm cooler than 100 degrees? What does the steam do? Yeah, well, it condenses, right? It turns back into a liquid. When it does that, what happens to all the energy it had as a vapor? It releases it into you, okay? And you get a deep tissue burn, all right, from steam because it releases all of that latent heat that it was carrying into your tissue. That's why steam burns you way worse than water does, okay? All right, so the specific latent heat of vaporization for water, 2,260 joules per gram. 1 milliliter of water requires 2,260 joules of energy in order to be vaporized. Okay, is that a lot? Okay. I'm going to assume you all had a shower this morning, okay? And I won't embarrass anyone if you didn't, but I'm assuming you all did. When you get out of the shower, you feel cold, right? Okay, why? A little bit, but I mean, you don't feel cold if you're dry and standing there. Okay? Why do you feel so much colder? Because you're wet. Because the water's evaporating. Where's it getting the energy to evaporate from? You. Okay? That's how sweat works. All right? When you sweat, the sweat evaporates. And when the sweat evaporates, it takes energy from your body to do so. Everybody follow me there? Okay? And so it cools you off. Right? Does it feel like if you're pouring, dripping with sweat, and you go stand in front of a fan, do you cool off even faster? Right, because that increases the rate of evaporation, right? And so, oh, you feel great. Stand in front of that fan because all that sweat is evaporating. You smell awful, okay? But okay, the sweat's evaporating and you feel much cooler, and that's a good thing, right? In the summertime, if it's blazing hot outside, you will probably feel really hot if you just lay there in the sun. But if you get up and move around, you probably won't feel as hot because it'll increase the evaporative rate, okay, of your sweat. And as a result, you'll feel cooler. Okay, it's a little bit counterintuitive, but okay, it works. Okay, is that making some sense there, guys? Is this a lot of energy then? All right, now let's imagine you've got this cloud full of water vapor. It probably has millions of liters of water in it. Is that a lot of stored energy? Yes, okay? That's why latent heat can transfer so much energy from place to place. It takes a lot of energy to evaporate water. All right, and then when it condenses back, it releases all of that energy back into the new environment. All right, so back to this example here. So now we're at this point, we have liquid water. Okay, so we're right here, we have liquid water, it's beginning to boil, and I want to calculate how much energy is required to turn all of that liquid water into steam, into water vapor. All right, so I've got to use this formula. E equals MLV. All right, are these formulas very hard to remember? They'll be on your formula sheet anyway, but okay, they're not hard to remember. Okay, LV, like we said, this is LV here, 2,260 joules. Okay, M is the mass, and we already said that the mass we were working with was 500 grams. All right, so E equals 500 times 2,260 joules. $1,130,000 joules. Okay, is that way more than all the other steps combined? It is. Okay, evaporating water takes more energy than all the other steps combined. Okay, it's a huge amount of energy to change the state of something into a vapor. Right, and that holds true for most materials. A lot. Okay? Because it's not just the water, right? If you actually to vaporize a person completely, you've got to vaporize sinew, bone, and those have much higher vaporizing points. Okay. All right. It disturbs me a little that you want to know that, but okay. All right. So 1,130,000 joules. So now I've got my water over here. It's a vapor at 100 degrees Celsius. If I continue to add heat, what will happen to the steam? It'll get hotter. Okay, steam can increase in temperature well above 100 degrees Celsius. If I kept adding heat, eventually it would turn into plasma, but that's something we don't even deal with. Okay, so I want to calculate now how much energy is required to heat this steam from 100 to 125 degrees. What formula do I use for that? E equals mc delta T. Right. Anytime temperature is changing, I use the formula that involves temperature change. Okay, so we have 500 grams, okay, times the specific capacity of steam, 2.02, pretty sure, okay, times 25 degrees Celsius. All right, 25,250, is that right? 2.02. All right. So this is kind of where this leads to. On an exam, what I'm normally going to ask is calculate the amount of energy required to turn X many grams of ice into water at this temperature. Right? Then you've got to remember this diagram. Right? I will not give you this diagram on a test, but this is the diagram you need to remember. I'm assuming that you have not been living under a rock your entire life and you know that ice melts at 0 and water boils at 100. Okay? Those are things I expect you to know. Okay. So what we have to remember here is that anytime temperature is increasing, we use E equals mc delta T, and make sure the only trick to that is using the right C, because ice, water, and steam all have different specific heat capacities. All right, that's back to that polar nature of water thing. Okay, water's weird. All right, and then then anywhere where the line is flat, where it's changing state, you have to use one of the E equals ml formulas, either LF or LV, depending on what part of the graph you're dealing with. Okay. What we just did is the biggest one you could do. Take it from ice to steam. Okay. That has the most steps, 5 steps. Right. All right. So if we wanted to find the total here, okay, we would add up all the numbers we had previously calculated. So we would have 166. 166, 500 plus 210,000 plus 1,130,000 plus 25,250. All right, so to take that 500 grams of ice from minus 25 degrees Celsius to 125 degrees Celsius takes 1,531,750 joules of energy. Okay. It's a lot. Okay, when you think about having to take a half a liter of ice and turn it into steam, okay, that's a lot of energy you'd have to put in to do that. Okay, does that seem terribly difficult? Okay, I think you guys can probably handle that, right? Okay. So, putting ice cubes in your water or your drink or whatever it is you have, okay, your pop, whatever. When you put ice cubes in there, they're probably below 0 degrees Celsius, right? So they absorb a little bit of energy from your drink in reaching 0 degrees. Where do they absorb the majority of the energy, though? Not for raising their temperature, but mostly for melting. Okay? As they slowly start to melt, they continue to absorb large amounts of energy from your drink. Okay? And that's what keeps your drink cold for longer. That's why you pack your cooler, if you're going camping, you pack your cooler full of ice. Okay? It's not that the ice is terribly cold. It's 0 degrees Celsius almost immediately after you put it in the cooler. But it'll melt for a long time because it can absorb a lot of energy while it melts. Okay? I mean, you wouldn't just go, oh, well, I've got this 0 degrees Celsius water. I'll just throw it in the cooler because it's cold. Okay? Can that absorb as much energy as ice? No, it's already in a liquid state. Okay? It already has more potential energy than the ice does. So the ice can absorb more heat. It can keep your stuff in your cooler cold for a longer period of time. Okay? It was common sense to know you put ice in a cooler before, and at least now you know why. Okay? Everybody with me? Okay. And sweat, we already talked about that. Your body sweats. Why does that cool us? Because it takes a lot of energy to evaporate water and turn it into a vapor. Okay? And to do that, that energy comes from your body, makes you feel cooler. That's also why you want to dress in layers if you're doing something like cross-country skiing or hiking and it's cold. Okay? Because as you work, you start to sweat. All right? You need to start taking off layers before you get too wet. Okay? Because if you get wet and then you stop, what'll happen? You'll get really cold because that water will still continue to evaporate. Okay? But you're now not exerting yourself anymore, and you get cold, you get hypothermia really, really quickly. Okay? The enemy of staying warm in the cold is sweat. Okay? You do not want to sweat if it is cold. Okay? You guys all know what that's like, right? You get the jacket sweats if you're out and you're shoveling, whatever. It's just nasty, right? And you take your coat off, and right away you start to feel cold again. Okay? You don't want to have just that one layer. If you have many layers and you start to feel a little warm, you take off one layer. Okay? Okay, I'm not sweating as much now. I'm good. Oh, I'm starting to sweat again. Take off another layer. Okay? And then when you start to get cold, you just put the layers back on, but they stay dry that way. Okay? And then you don't have that problem with being wet later. All right? Making sense? All right. Now, if you're just dripping with sweat, but you're not moving around very much, is the sweat doing very much for you? No. Okay. This is the problem that a lot of athletes have in sports where they have to wear a lot of equipment. Okay, because when they're wearing a lot of equipment, the air doesn't flow through the equipment very well, and so it's difficult to evaporate the sweat. Nikolai Habibulin used to be a goaltender for various teams, Chicago and Edmonton, and I think he's back in Chicago now. Okay. Anyway, he sweats like crazy. He has holes drilled in the bottom of his skates to drain the sweat. Okay. And they actually caught it once on a goalie cam. And one of the cameras in the back of the goal that actually sees whether a puck went through or not. And they actually caught the sweat dripping out of the bottom of his skates. Okay, this guy loses 10 to 15 pounds in a game. Just water. That's how much he sweats. Okay, he has to get his glove, his blocker, and his mitt changed about once a period because they're just soaked. Right? Because he doesn't get to move around, right? Like, it's hard work when he gets action, and people are shooting pucks at him, and he works really hard, but then he's just standing there, okay, the rest of the time. And so that sweat doesn't get a chance to evaporate, and it just pours off of the guy, okay? It's disgusting, actually. Okay. I played basketball in high school with a guy who was like that. He couldn't wear his uniform during the warm-up, or it would be soaked, okay? 2 minutes into the game, it's just dripping. You didn't want to play defense on him because he was slimy all the time. Okay, but it's important to sweat, but some people sweat more than others, right? There's this point where continuing to sweat ceases to be productive. Okay, but you don't want to sweat too little either because then your body temperature goes up and that's not healthy for you either. Okay, all right. Gardeners will often spray their crops before a frost that prevents the products from freezing. How? John? Well, we don't want it to absorb energy because if it absorbs energy, the fruit gets cold. Okay? But if you have a thin layer of water on the fruit and the temperature drops below freezing, will that water freeze? Where will the potential thermal energy from that water go? Into the fruit. Okay? Now that only works if it's a mild frost. Okay? If it's like -2, -3. Okay? It's not going to work if it drops down to -10. Okay? Your tomatoes are toast at that point. But it does work if it's going to be a mild freeze, and that's usually what people who grow apples and strawberries and stuff like that deal with, is very mild freezes, and that will help to prevent frost damage to their crops because it uses the fact that as water freezes, it has to release its thermal potential energy. All right, we talked about number 4 already. Obviously, ice is better at keeping water or at keeping food in a cooler cold than water because it has less total thermal energy. It has not changed into a liquid state yet and still has to absorb a lot of energy to do so, and it absorbs that energy from your food. Okay. All right, the rest of those you can solve. Okay? They're just like the example we did. Anytime you end up with a question that talks about water being heated and there's a state change involved, the first thing you want to do is draw a rough sketch of that diagram we had. Okay, the heating curve of water. The flat part here is 0, the flat part here is 100 degrees. Okay, and mark on it your starting and ending points. And then you'll know which calculations you have to do. So for question number 5, it says, how much heat is given off when 2 kilograms of water at 0 degrees freezes into ice at 0 degrees? All right, so I'm starting here. That's water at 0. This is ice at 0. Okay, how many steps there? It's just 1, right? Okay, it's not changing temperature at all. It stays at 0 the whole time. What formula do I use here to calculate energy? MLF equals MLF. Okay, up here I use E equals MLV. Okay, and any of the parts where the temperature is going up, I use E equals MC delta T. Right? I should have an upward part there too. All right, so for this one here, all I have to do is E equals MLF. Okay, 2 kilograms is how many grams? 2,000. Okay, times LF, which is 333. All right, that gives us 666,000 joules. All right, is that making sense? Okay, so just mark on your heating curve that you draw. Okay, it's an easy shape to remember. Mark off where you're starting, mark off where you're ending, and then you'll very easily be able to figure out what formulas you'll have to use, and you add them all together at the end. All right, so I'll give you a few minutes here. You got about 5 minutes left. You'll probably be able to get 6 and 7 done. Okay, we'll look at a few more tomorrow and see how we do then.